Okay, so in this section, we are going to find the derivative of a logarithmic function, and then we will talk about logarithmic differentiation. So you may remember that we defined the logarithm as an inverse function, and that was the inverse of the exponential. And so how we deal with taking the derivative is going to be really similar to how we dealt with the inverse trig functions. Okay, so what we did there is we said that that y was equal to, here we want to take the derivative of log base b of x, right? And so we're looking for y prime, and this is true if and only if b to the y is equal to x. Okay, and this was the definition of the logarithm. And now we can use implicit differentiation to take the derivative of both sides and find y prime. Right, so first step is to take the derivative of both sides. On the left-hand side, we have an exponential function. And remember, whenever we have y as our variable, we also need to multiply by y prime when we're taking the derivative because of the chain rule. So first, the derivative of the exponential for a base b is natural log of b times b to the y, and then we multiply that by y prime, right? Okay, and then the other side is just the derivative of x, which is just 1. And so this equation is pretty simple to solve. It's just we need to divide by this stuff to get y prime by itself. So we get 1 over the natural log of b times b to the y. Okay, now that is an answer, and it's pretty easy to get this back into a form where we only have x in it instead of y, right? So what we can do is just use this fact up here that b to the y is equal to x. So really we just need to replace this b to the y with x, and then we'll have our answer. So this is going to be 1 over natural log of b times b to the x. Okay, so that is the derivative of log base b of x. So I'm going to go ahead and put that in our chart. So these are all the derivatives that we've learned so far, and then we have a new one, and this is natural log of b times b, oh sorry, I did this wrong. This shouldn't be b to the x, this should be x. Okay, so instead of b to the x, we get natural log of b times x. And then, of course, in calculus, we like to use the natural log function a lot. So let's just note that if y is equal to natural log of x, so if this is the case, then y prime is 1 over natural log, the base here is e times x, but natural log of e is just equal to 1. So in this case, when we're using the natural log, the formula is even nicer. It's just 1 over x. And a lot of the time we do use the natural log because of this nicer formula for the derivative. Okay, so we have those two formulas now for the logarithmic functions. There's one more thing that I wanted to mention. It doesn't come up that much in Calc 1, but it does in Calc 2, so I just want to make a note here. So when we look at the logarithmic function, remember that this is only defined for x greater than 0, right? So when we write this down up here, this is for x greater than 0, because that's the domain of the logarithm. What we can do is sort of extend the domain and have this function be defined for more values. And how we do that is we do, so I would say consider the function natural log of absolute value of x. And if you graph this, what you'll find is that we know what the natural log looks like for positive values of x. This would just be equal to natural log of x for positive values. Maybe I should move this over a little bit, right? So on the positive side of the x-axis, it looks like this. That's the natural log curve. And on the negative side, so we can't have x equal to 0, so that's not allowed, but we can have here when we take the absolute value of a negative number, that's equal to that negative number, which gives us a positive number. So here, if we were to rewrite this as a piecewise defined function, this is how we would do it. And see, on this side, what happens is we get natural log of negative x, and if you were to go ahead and graph that for x less than 0, it would look like this. So we didn't talk about graph transformations at the beginning of this class, but it is the case that when you have a negative in front of your input variable, what that does is it flips the graph over the y-axis, so it just reflects it straight over, and so we get this two-sided. They don't look exactly the same, but they actually should be exactly the same on either side of the y-axis. And so we get something like a logarithmic curve with a domain that's been extended. And it's also the case for this extended domain that the derivative is still just equal to 1 over x. And we can see that by, well, first we have our piecewise defined representation of this function. And then if we want to take the derivative, since we have two different pieces, we don't have to worry about what happens at 0, right? It's not defined there, so there's no derivative there. And then for the separate pieces, we can just differentiate them separately. So the derivative of natural log of x would be equal to, for the first piece, that's if x is greater than 0, we would get just 1 over x. That's just the natural log function that we just found the derivative for. And then for the next one, this is a negative x inside of the natural log function, so we can just use the chain rule to differentiate that. So this is if x is less than 0, what we get is first 1 over negative x times the derivative of negative x, which is just negative 1. So you see that this simplifies to 1 over x if x is greater than 0, and 1 over x if x is less than 0. And it turns out that 1 over x is defined for all of these values except at 0, so this is really just a more complicated way of writing the function 1 over x. Okay, so we get that the derivative of natural log of absolute value of x is also equal to 1 over x. So I'll put that in here. Like I said, it won't come up that much in this class, most likely, but it's good to know. So the difference between these two is just a difference of domain. So they'll agree on the right-hand side of the x-axis, the positive part, and then on the left-hand side, this function has an extended domain, and the derivative is just the same. Okay, so yeah, I think I'll stop here and do some examples of taking derivatives in the next video.